Okay, so in the next two videos, I want to talk about how we determine rate laws. And there are two methods. First is called the method of initial rates, it's described in Atkins 17A. And then the second is called integrated rate laws in Atkins 17B. We're going to start here. I'm talking about the method of initial rates in this video. And here's the basic idea. What you do is measure the reaction rate at a variety of reagent concentrations. And you figure out how the reaction rate changes with concentration. When you do it, you typically do it with one reagent in large excess so that its concentration is effectively constant and doesn't change anything. So here's an example. It's a sort of weird gas phase reaction to make iodine gas. You might imagine measuring the rates at a variety of concentrations. So down the column, you can see that I'm changing the iodine concentration, and then across the row, we're changing the argon concentration. Argon concentration is 100 times bigger than the iodine, so that it's relatively constant. And the way you start to handle this is to make some inferences about reaction or rate law. Okay. So let me show you. If I go from here to here, the concentration doubles. If I look at these two, right, this is 8.7 times 10 to the minus 4. If I double it, that's like 17 times 10 to the minus 4, or 1.7 times 10 to the minus 3. This is not 1.7. In fact, if I double 1.7 again, you would end up at 3.4. So I've doubled it twice. This has gone up a factor of 4. If I look down here again, concentration has gone up 2 times. If I compare these two, again, doubling this is 7. If I double it again, I get 14. So this has gone up 4x. Right? Looking down a column, or I should probably say analyzing it, it looks like V is proportional to I squared. Right? I double the concentration and the reaction rate goes up by a factor of 4. Now if I look across a row, and I'll do this in a different color. I'm going to pick these two data points, right? Because 5, this is 10, I'm just doubling it. Right? I like numbers that I can handle. So in this case, I've increased the concentration of argon by a factor of 2. 4.3 times 2 would be 8.6. This looks like it's going up 2x. If I look at this set of conditions, 1.7 times 2 is about 3.4. So this is 2x. I double concentration and the rate goes up by a factor of 2. So looking across a row, I would say that V is proportional to argon raised to the first. Right? Double concentration, it doubles. Putting it all together, this is the one I want. We would say then that V equals K, some constant, I squared R, argon, sorry. It's an overall third order reaction. All right, once we've determined the rate law, we have to figure out the rate constant. I don't know why this slide is here. So let's go to this one. How do we figure out the rate constant? These types of problems are amenable to graphical analysis. So the best way to do it is with graphical analysis. And here's the overall rate law. The way that you usually handle this is because argon is in such large concentration, I can suck argon times the rate constant up into some new pseudo rate constant. And I would get that V is equal to K, this pseudo rate constant, times I squared. So this suggests I would plot V versus I squared and get a straight line. Right? So that's shown here. V versus I squared. I get these different straight lines. They all have different slopes because there's a different argon concentration associated with each one of these. Once I have these slopes, the pseudo rate constant, I can look at the secondary equation. And now I'm going to plot K prime, the pseudo rate constant, versus argon. And indeed, you get a straight line which goes through 0. I can look at the slope of this. And if I analyze everything correctly, what you will find at the end of the day is that the rate constant is 8.7 times 10 to the 3 per millimolar square per second. Units are important in rate constants. All right, that's it. That's my next slide. So I'm going to stop here, short one, and I'll see you next time for this other method.